Hey there, we're going to go over some angular momentum notes and then work a practice problem together as well. And if you recall back from our linear momentum unit last semester, the linear momentum was related to the mass and velocity of the object. And we had the equation P is equal to mv, where P was my linear momentum. And we just had that as kilograms times meters per second. And so very similar to this, we have a new equation for the angular momentum of an object that's rotating. And that equation is L is equal to, instead of mass, since we're rotating, we're going to have that rotational inertia. And instead of the linear velocity, we're going to have our angular velocity, omega. So this L here represents my angular momentum. And the unit that we have for that ends up being kilograms times meters squared per second. And also back in our momentum unit, we had that impulse momentum theorem. And what that told us was that some net force, some external net force exerted for a period of time equals a change in linear momentum. And we have something very similar for an object that's rotating, but instead of it being a net force that causes that um, change in momentum, it's going to end up being a net torque. So it's a very similar equation, but it's going to be my net torque exerted for a period of time will equal a change in angular momentum. Okay, so these are the two equations that we have for angular momentum, right here and right here. And also in our momentum unit, we had conservation of momentum. And during the conservation of momentum portion, if there's no external force, then your momentum was going to be conserved. Well, just like that with angular momentum, if there is no net torque, then the angular momentum L is conserved. So it's a very similar concepts to linear momentum with angular momentum. We're just using a few different terms here. Instead of net force, we're using net torque. Instead of mass, we're using that rotational inertia. And instead of linear velocity, we're using this angular velocity. So let's look at a couple examples. We'll kind of draw it out and see what happens to the angular momentum in some different situations. So let's draw a wheel here. And let's say that this wheel is rotating clockwise. Okay, so it's initially rotating clockwise. And then we apply a force here perpendicular to the bottom portion of the wheel. So we have some force here. Now, since it's rotating clockwise and we're applying a force that's going to be counterclockwise, then that would result in a decrease in my angular momentum. In another situation, if the wheel is still going counterclockwise, or I'm sorry, clockwise, and then we apply a force here at the top of it, so that would cause it to rotate clockwise, so we would end up with an increase in angular momentum. And the last situation here, let's say we have this same wheel, still rotating this way, and now we apply a force right here in the center of it, then this force would not apply any torque, so the torque is equal to 0. So that would result in a constant angular momentum. So there's just a few different situations where you can see how a force could change your angular momentum. And the key thing is if there's no net torque, like in this situation here, then your angular momentum is going to be conserved. We can also see that in a real life situation if you've ever watched figure skating. So I'm not very good at drawing, but I'll try to draw a little stick figure here. And let's say this person is figure skating and they have their hands spread out real wide and they start to kind of rotate and spin in a circle on the ice skating rink. And if you've ever watched any of those events, what they do is they bring their arms inward, and when they do, so now their arms are inward, and when they do, they actually start to rotate faster. Okay, and this whole idea is this conservation of angular momentum. So if we look at the first situation, L is equal to the rotational inertia times the angular velocity. And the same equation can be applied for afterwards. And by tucking their arms in, they're actually going to decrease their rotational inertia because they're bringing the mass that's being distributed closer to the axis of rotation. The angular momentum is going to be conserved, so that means that your angular velocity would have to increase. And so that's the whole idea with the figure skaters, is that they're changing their moment of inertia. Momentum, the angular momentum is conserved, so they're going to increase their speed. So let's look at a practice problem. And this one says that a boy is standing on a merry-go-round which is rotating 10 radians per second. And in this case, the moment of inertia is 100 kilograms times meters squared. Remember, the problem will always tell you what it's equal to, or they'll give you that equation. It says the boy then walks to the edge of the merry-go-round, and it changes the moment of inertia by 25 kilograms times meters squared. And the first question is, does this system rotate faster or slower? So same kind of concept that we were talking about with this figure skater. And so when the kid starts to walk towards the edge of the merry-go-round, the mass is being distributed further away from the axis of rotation. So that means that you're going to have an increase in your rotational inertia. So your I is going to increase. And momentum, angular momentum, will be conserved. This stays the same. We're having an increase in your rotational inertia, so that means that the angular velocity will have to decrease. So it's going to be moving slower. Then it says find the new angular velocity of the system. So we're going to apply this idea of conservation of angular momentum. So we're going to set the angular momentum before equal to the angular momentum after. And let's substitute in our equation here. So we have I omega equals this new rotational inertia and this new angular velocity. And we're solving for the new angular velocity. So let's divide both sides by the new rotational inertia. And that cancels that out. So we could find the angular velocity. It's going to equal I omega divided by this new I. And since the rotational inertia increased, initially it was equal to 100 kilograms times meters squared. So that means that the new one, it increased by 25, so it's 125 kilograms times meters squared. Now we can plug in our numbers to calculate the new angular velocity. So it's going to be 100 kilograms times meters squared. Multiply that by that initial angular velocity, which was 10 radians per second, all over 125 kilograms times meters squared. And when we plug that in, you should end up with 8 radians per second. And if we're comparing the angular velocity, it did indeed decrease because now it's rotating at a slower angular velocity. Now there's one more concept we're going to kind of talk about, and that is that non-rotating objects can also have angular momentum. So let's look at a situation. So let's draw a bar. get this line on here. Okay, we'll just leave it. So here is, say, a rod, and let's say it's fixed over here on the left end, so that's your axis of rotation. And let's say we have another ball down here, and it's rolling towards this rod. Well, when it runs into it and it collides with this rod, it's actually going to cause this rod here to rotate counterclockwise. So this ball here, even though the ball itself may not be rotating, it does have angular momentum because it's causing this rod to rotate when it collides with it. And so our equation for that is angular momentum is equal to the moment arm, so the distance from the axis rotation to where it's going to hit it, times the linear momentum p. And remember, p is equal to mv, so we could substitute in the mass times velocity for this momentum here, giving us the equation angular momentum is equal to rmv. So an object that is not rotating can still have that angular momentum if it's perpendicular to that moment arm. So in other words, if I had another ball right here and it was moving towards this rod, this one does not have any angular momentum because it's moving parallel with that moment arm. So there's some simple concepts there with angular momentum, and we'll do some more practice here in class using these equations as well.